Guys, welcome to the 5.4 notes. We're going to take a look at more Riemann sums in these videos. So we did left endpoint and right endpoint Riemann sums in 5.3. Today we're going to look at two other ones, the midpoint Riemann sum and then also the trapezoidal Riemann sum. So if we take a look at example 1, it says consider the curve y equals negative 1/3 x squared plus 6 over the interval with a closed interval from 1 to 4. It says using the midpoint rule and 3 subintervals, approximate the area under the curve. So what we're going to do in this point is when we use the midpoint rule, we're going to use the midpoint of each subinterval. So we're going to use the midpoint of each subinterval to determine the height of the function. All right, so now, like other Riemann sums, the midpoint Riemann sum, we're still using rectangles to approximate the area under the curve. So to find the area of the rectangle, we need the width and the height, or the base and the height essentially. So we're going to find the width by taking our interval, and we're going to go 4 minus 1, and then we're going to divide that by the number of subintervals, which is 3. So in this case, that would be 3 over 3, which is 1. So each of our intervals is going to have a width of 1. Now, our first interval is going to start at 1 and end at 2. What we want to do is find the height at the midpoint of that interval. So halfway from 1 to 2 is 1 1/2 or 3/2. So we want to use the height at 3/2. All right. Our next interval would go from 2 to 3. So the midpoint of 2 and 3 is 2 1/2, which is 5/2. And our last interval is going to go from 3 to 4, which has a midpoint of 3 1/2 or 7/2. And I'm just using fractions, a little bit easier to plug those in. So at that point, we're going to plug those into our function. So we have negative 1/3 times 3/2 squared plus 6. And if we simplify that, let's see what we get. We get 9/4 minus 1/3. 9/4 times negative 1/3. So that's negative 9 over 12. And then if we get a common denominator of 12, we're going to get 72 over 12. So negative 9 plus 72, that's going to be 63 over 12. And then we just continue that process here. So we've got negative 1/3. This is going to be 5/2 squared plus 6. So that's 25/4 times negative 1/3 is negative 25/12. And then that 6 is 72/12 again. So that combines to give us 47 over 12. And if we plug in 7/2, we're going to get 49/4, which is negative 49/12 when you multiply by the negative 1/3. And then negative 49 plus 72 is going to be 23 over 12. So that becomes the height of our function. So basically what we're doing is we're taking the height of the function at the midpoint, which is going to correspond to there, and we're creating this rectangle. So there's the first rectangle. The second rectangle, we take the height between 2 and 3, which is about there. And we're going to have that rectangle. And then the midpoint of the third rectangle is approximately there. So what we're doing is we're using those 3 rectangles to approximate the area under the curve on those intervals. All right. So the area is basically going to be the width, in this case, times f of 3/2 plus f of 5 halves plus f of 7 halves. And if we plug in our corresponding values, our width was 1. F of 3 halves was 63 over 12 plus 47 over 12 plus 23 over 12. And if we combine those, we get 133 over 12. So the area under the curve of that function from 1 to 4 is approximately 133 over 12 units squared. And that's how we're going to use that midpoint Riemann sum. So, I mean, again, the midpoint rule, we're still just using rectangles to approximate the area, so it's the width, all right, and then times the height. So f of a plus f of b plus f of n, depending on how many subintervals that we're using. The key thing is to understand that a is the midpoint of your first subinterval, b is the midpoint of your second subinterval, and so forth. Okay, guys, that takes care of example 1. Now, we'll take a look at example 2. So when we look at example 2, it says consider the curve y equals negative 1/3 x squared plus 6 over the closed interval 1 to 4. Using a trapezoidal rule and 3 subintervals, we want to approximate the area under the curve. So now, as we take a look at this, let's just kind of visualize what's happening. So with the trapezoidal rule, we're going to basically be using trapezoids on our subintervals. So it's going to look like this. The next one's going to look like that. All right, and our last one is going to look like that. And again, we're using the area of those trapezoids to represent the area under the curve. Well, to do this, we need to make sure we understand the formula for the area of a trapezoid. So the area of a trapezoid is 1/2 the height times the sum of the bases. So base 1 plus base 2. All right? So one thing that's going to be important for us to understand is that in this case, when we're applying it to Riemann sums, is the height is going to be on its side, which is going to be the width of our interval. So the width of our interval is going to end up representing the height of that trapezoid. Okay? Because with the trapezoid, you have two sides, exactly one pair of parallel sides, and the distance between those two parallel sides is going to be the height. So in this case, you know, you can think of, in terms of some different values, this is base 1, all right, the first side. This is base 2, this is base 3, and this is base 4. Now, one thing that's going to be important to understand now is how does that apply to the Riemann sum? So the trapezoidal rule of this particular Riemann sum, the area is going to be 1/2 times the width. Now, remember, we're talking about the width of the intervals. Now, what ends up happening is, you know, f of a is going to represent base 1. So it's going to be f of a plus f of b is going to represent base 2. So it's f of b. If I stopped right there, that would simply represent the area of this trapezoid right there. Well then, if we wanted to include the next trapezoid, all right, we're assuming the base is, or the width is uniform as we do this, then we're going to add the area of the next trapezoid, which is going to be f of b again. Again, I'm calling that a, that b, that c, and that d for these purposes. But f of b plus f of c. So that right there would now be taking care of that trapezoid. And then we now have another trapezoid, which would have bases, in this case, f of c and f of d. Right. Now, we're going to simplify this here in just a minute. But, again, the last one that I just found, that would correspond to this trapezoid in this example. So, those two would represent base 1 and base 2 of that furthest trapezoid on the right. And I'm just going to color code this for you guys a little bit. Those two right there would represent the trapezoid in the middle. And those two right there are going to represent the trapezoid on the left, the first one. Well, what you guys hopefully notice is that f of b shows up in those two places. F of c shows up in those two places. So when you actually are using this trapezoidal rule, the formula that we're going to use when the widths are equal, it's 1/2 the width, all right, times, well, the outer heights, the outer bases are only used one time. So it's going to be f of a plus. The inner bases are going to be used twice because there's going to be two separate trapezoids. So it's 2 times f of b plus 2 times f of c. And that's going to continue until you get to the final trapezoid. And that endpoint value is only going to be used one time. So this is what we look for in terms of a formula for a trapezoidal Riemann sum. So now, to apply that to this particular problem, all right, we're going to have to find some values. So we need to identify the width. So the width is going to be 4 minus 1 divided by the number of subintervals. So again, that's going to give us 1. Now, for this example, the heights that we're going to need are f of 1, f of 2, f of 3, and f of 4. Okay, those are the 4 heights that make up the bases of those trapezoids. And again, you just plug into the formula. So we got negative 1/3 times 1 squared plus 6. Over here, negative 1/3 times 2 squared plus 6. Negative 1/3 times 3 squared plus 6. And negative 1/3 times 4 squared plus 6. All right, as we evaluate those, we're going to get what? Negative 1/3 plus 6. So that becomes 17/3. Here we're going to get negative 4/3 plus 6, so that's 14/3. Negative 9/3 plus 6, so that's going to be 9/3. And negative 16/3 plus 6 is 2/3. So now, as you plug that into the formula, our area is going to be 1/2. All right, our width of every interval is 1, so it's 1 and then times. Now here's where the bases come in. F of 1 is only the height or the base of one of the trapezoids. So we're going to use 17/3 one time. The inner two values are used twice because they're bases of two different trapezoids. So we have 2 times 14/3 plus 2 times 9/3. And then the f of 4 is only the base of one trapezoid, so that value gets used once, 2/3. As you go through to simplify this, when you combine that, what's this? This is 17/3, 28/3, 18/3 plus 2/3. And as you combine those combine to give you 65/3. And when you multiply that by 1/2, you get 65 over 6, which is approximately 10.833. And that is how you can use the trapezoidal rule to find the area under the curve. All right, guys, make sure you take a look at part 2 of the video. That's it for part 1.